In this video, we'll take some of the principles that we just talked about, and we'll look at how we actually analyze structural elements, how we use some of the vector geometry and some of the principles that we've talked about equilibrium to actually get inside and think about what's going on inside individual structural elements. To do this, we will go back to the idea of a free body, where we'll take a structural element and basically reduce it to a point or an abstract element like a line. And we'll think about both the loads that we're putting onto it, gravity loads in particular in this case, and the reactions that we would like to put in there, equal and opposite to the sum of the loads that will keep it in place. And remember, a vector has magnitude, direction, and sense. So the arrow is pointing in a given direction. It's positive or negative depending on which way the heads and tails go. And crucially, it has a length that's proportional not to something in space, but to the amount of force that we're putting onto our little free body here. And the goal in statics always is to make sure that whatever the loads are, we sum up all the loads, we put them on the free body, we figure out what the total of those are, and then we figure out what the equal and opposite force would be. And that's the reaction. That's what we'll be asking the structure basically to provide. Now, the principles of free bodies mean that we've abstracted them, we're putting vectors on them, and because those vectors are mathematical entities, we can use a little bit of algebra, and in this case some trigonometry, to figure out both the angles and the magnitudes of the resultants. In this video, we'll just be working with translational equilibrium, so all we're doing is looking at the sum of the arrows, the resisting arrow that pushes back, and how we'll keep things in place in space. And in the next video, we'll show how rotational equilibrium helps us analyze beams, how we can actually use the principles of equilibrium to figure out what's going on in a structure. Now, 2 points to make before we get into this. One is that this is going to be pretty mathy, some trigonometry, some algebra. This is going to sort of seem like one long story problem. If it doesn't come to you right away, you can go back and, of course, review the lectures. Keep in mind that the reason we're going through this isn't because you as an architect will ever have to design and calculate structures. We leave that professionally to the structural engineers. But what I really want is for you to understand kind of what's going on, to get some of the nuts and bolts behind things that will actually hopefully seem pretty intuitive. And when you're sitting across from a structural engineer in a design meeting, to understand what they're going to be doing to calculate the structure that you all are talking about. So it's more a kind of understanding and awareness of how the math works. And if math isn't your strong suit, brushing up on a little bit of trig and going through some of the fairly simple problems that we'll put in the lab problems, hopefully that'll just give you a kind of fluency in the way that some of this works. The other thing to say is that we're taking equilibrium, which we've talked about so far as kind of a problem, right? We don't want our buildings to move. And in all of these cases, we're actually using that as a tool. We're saying that we're going to take the desired outcome, which is that our buildings aren't going to move, and we're going to use that as a sort of thought experiment, figuring out how we can actually keep them in equilibrium, right? So we're sort of turning the tables. Instead of saying, oh, buildings falling over are a problem, we're going to start by saying we're going to figure out what it takes to keep the building from falling over and go from there. Now, to do that, we're going to use trigonometry, and in particular, we're going to look at the principles of equilibrium in kind of mathematical notation. So when we write these sets of equations here, what each of these are saying is sigma means the sum, so add up all of. Fx is going to be forces in the x direction, horizontal direction. Here, the sum of all forces in the y direction, and here the sum of all forces in the z direction. Now, we'll typically, in our problems, just be doing two-dimensional things, so we can ignore z. We're just going to be looking at forces in the x, horizontal, and the vertical y direction. Later, when we talk about beams, we'll be writing these equations to start out with. And what these all say is that the sum, again, sigma just means add everything up that you can think of. all of the moments around the x-axis, all of the moments around the y-axis, all of the moments around the z-axis are 0. And the reason we'll start with these is that these give us a kind of laundry list of the conditions that we have to look at, right? The translation in all three axes should be 0. The moments or torques around all three axes should be 0. And then we can go in and we can actually think to ourselves, okay, what forces are pushing on the free body in each of these three axes? We'll do a set of equations that are basically a kind of laundry list. And we'll add those up together in each axis and figure out what the force in each axis will have to be to resist that. We can then go through and we can figure out both the angle and the magnitude of that vector. So these look a little intimidating. The Greek letter sigma just means do the laundry list, right? Come up with all of the forces in each of these three axes that you can think of by looking at the situation and solve them for 0. So remember too that when we're working with vector algebra, this lets us add forces together. So here we have two forces, P1 and P2, that are working on the free body, and we can add those up in a couple of ways. We can break them down into horizontal and vertical components, or we can simply put them head to tail and figure out what the resultant would be. So you can either do this using algebra and trigonometry, or you can go into AutoCAD and draw the arrows to scale and figure out graphically what the resultant would have to be. In all of these cases, what you find is that when you put the arrows head to tail, you end up, if you connect the tail of the first arrow with the head of the last arrow, you get a resultant, and that is the sum total of those two forces. So note that P1 and P2 have opposite senses in the vertical direction, in the y direction. So the resultant is actually going to be somewhere between the vertical component of P1 and the vertical component of P2, right? See how it splits the difference? Notice too that P2 has a horizontal component in the x direction, and P1 has no horizontal component. So the horizontal component of our resultant is going to be equal to the horizontal component of P2, right? P1 doesn't contribute anything to that. The sum of forces in the x direction is just going to be that of P2, right? Because P1 is perpendicular to it. So there are tricks like that that we can use when we're looking at free bodies to think about how to simplify things, right? Or how to keep track of things. So the resultant that we want is going to be equal and opposite to that. And here, this is the reaction that would be necessary to resist the combined loads of P1 and P2. And again, we can figure that out mathematically, add the vertical and horizontal components together, get an angle and a magnitude, or we can simply draw that in AutoCAD as the resultant of two accurately scaled arrows, flip it around, apply it to the free body, and know that that free body will now be in translational equilibrium. And notice that we're just working in the x and y axes, right? There's no z axis, there's no in and out of the screen. We're keeping it fairly simple here. So the other thing to remember is your high school trigonometry, and in particular the relationship between angles and the three sides of a right triangle. And we'll keep everything with right triangles so the trigonometry stays a little bit simple. These are the only three things that you really have to remember: that the sine of an angle is equal to the opposite leg divided by the hypotenuse. The cosine is equal to the adjacent leg divided by the hypotenuse. And the tangent of an angle is equal to the opposite side over the adjacent side. So if you remember these, and this is the mnemonic that I always put at the top of a piece of paper when I'm doing these: so katoa, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And if you print this slide out and sort of tack it above your desk, you'll have no problem getting through the free body exercises here that we'll do. So here's the problem that we'll actually dive into, and this is a cable structure being hung from above, two 100-pound weights suspended on steel cables and attached to a concrete slab with an angle between them of 60 degrees. And what we would like to do is we would like to figure out how these loads end up getting carried by the cables and how much stress and it'll be in tension, right? The loads are pulling on the cables. So how much tension will each of these cables feel, basically? And that figure will give us a number that will tell us what the reaction has to be in those cables. And later on, when we talk about strength of materials, that will help us figure out how large a cable we would need to carry each of these loads. So first of all, just from a simple stability standpoint, will the structure work? And if you do the thought experiment and think about 200-pound loads on 2 steel cables, the answer is no, right? That they would just clang together. The cables are flexible, and these 2 weights are going to try to find their lowest position. And so there's nothing yet to hold them at that angle, at that 60-degree angle. What we need is a triangle. We need something between them that will keep them from finding that lowest position. And this is going to be a strut, basically, down at the bottom that prevents them from coming any closer, but also from sinking any lower, basically. Note that it's a triangle. We know that that's a stable structure. And if we think through it, notice that the cables are still going to be in tension, right? The weights are pulling down on them. But now when we think about what we need to keep the weights from coming together, we realize that this strut is going to have to be in compression, right? The weights are going to push on the strut instead of pull on it. So we have elements here that can be cables that are in tension. We have an element here that's going to be in compression, right? The weights are going to push on it. And we'll talk a lot about why this is when we get to columns, but basically when we draw compression elements, we draw them a little bit thicker because they're likely to be more robust, heavier elements than the tension elements. So let's zoom in and let's look at the junction of the strut and the cable and the weight, and let's think about that point as a free body, right? So here is our abstracted point. We're looking at the kind of intersection of those 3 elements, and note that we're not really thinking of it spatially. We're not really interested in how big that connection is or what it looks like, what it's made out of. We're literally thinking of it just as a point in space. Now, the next thing we want to do is we want to look at all of the forces that might be acting on it. So anything that's going to push that point to the left, to the right, up, down, anything that's going to give it a force in the X or Y direction. So one thing we know that we have is the weight of the anvil itself. And this is going to be 100 pounds, and clearly it's pulling down, right? It's a gravity load. So we'll draw an arrow, and this will draw to scale, so 100 pixels or 100 millimeters, whatever you want, so long as we're keeping the scale consistent for each of the arrows that we draw. And then we have 2 other forces that are going to be working on that. One of them is going to be the force in the cable. We don't know what that is, but we do know what the angle is going to be. Right? The angle is going to be 60 degrees from the horizontal. And the other force that we know about is going to be the force that's in the strut itself. And we know that that's going to be at 0 or 180 degrees. Right? The way we've drawn it here shows that it'll be in compression. The arrows are pushing out from the center of the element. Note that the arrow is pulling toward the center of the element for the cable. That means that this is in tension, and the weight of the anvil is pulling down. So if we look at those 3 arrows, we've got a fighting chance of making this point stay in equilibrium. We have a force that's pulling down, the weight. We have a force in the cable that's pulling up, right? That's the tension in the steel. Because that cable is at an angle, that force is also pulling to the right, but notice that the force in the strut is pushing to the left. So the horizontal component of this vector and the horizontal component of this vector have a chance of canceling each other out. And that's what we're going to try to assume. That's where we're going to start and kind of backtrack and figure out what those forces need to be. Now, remember that we can rearrange those arrows however we want. So if we've drawn them all to scale and at the right angles, we can literally cut and paste them and come up with what we call a force triangle. And notice that we've basically here, because we don't know yet what the magnitude's going to be, we can draw those basically so that they end up being to scale. The weight of the anvil is 100 pounds. We draw an arrow at 60 degrees from the horizontal that has the same vertical component as the weight. And then here we've drawn an arrow that's the force in the strut that takes up basically the horizontal component of the force in the cable and takes it back to where we started, right back to the tail of the anvil weight arrow. Now, this will end up being a fairly simple triangle. That 60 degrees is going to show up here. The 30 degrees here is essentially the angle between the vertical and the force in the cable. Remember again, this is the weight of the anvil. This is the force in the cable. This is the force in the strut. And now, since we know that one of those legs has a length of 100 pounds, I know that sounds weird, but remember we're drawing magnitudes of forces, not spatial distances. We can actually use some simple trig to figure out what both of these two arrows are. We have the force in the cable, which we'll call F cable. We have the force in the strut, we'll call that F strut. And now we'll do some simple trigonometric equations to figure out, based on the angles there and the magnitude of the force there, what the remaining legs of the triangle are. Right, so we're solving for F cable and F strut. Again, remember our high school trigonometry, sine, cosine, tangent. And we can start by trying to figure out the force in the cable. So that is, we have the opposite leg here, the 100 pounds, and the hypotenuse here, the force in the cable. So sine equals opposite over hypotenuse. So sine of 60 will equal 100 pounds divided by the force in the cable. We can use algebra to move the force in the cable over here, multiply it by times 60 to get 100 pounds, and then we can use algebra again to put all of the numbers that we have on one side and all of the unknowns, in this case just one, on the left side. So the force in the cable is going to be equal to 100 pounds divided by the sine of that angle there, 60 degrees. We look up sine of 60, or just get it on our calculator, and we get the force in the cable is going to be 100 pounds divided by 0.866. And that is going to give us 115.5 pounds. And that rings true, right? This is a hypotenuse, so it's going to be larger than either of the two legs. 100 pounds there, 115.5 pounds there. And now we're going to try to find the force that's actually in the strut, in the compressive element. We could use the Pythagorean theorem if you're a fan of that, but since we've started with some trigonometry, let's keep going. Here we've got a case where we can use the tangent, right? We know the opposite, we don't know the adjacent, and we know the angle. So we can say that the tangent of 60 is going to equal opposite over adjacent, which in this case will be 100 pounds divided by the force in the strut. Again, we move things around so that we get all the numbers on one side and all the unknowns on the other. We end up with the force in the strut being 100 pounds divided by tan 60. Tangent of 60 is 1.73, so notice that the horizontal force is going to be less than the vertical force. And in fact, if we do the math, 100 divided by 1.73 is 57.8 pounds. So here we have the set of forces that will keep that point where the weight and the strut and the cable all meet in equilibrium. The 100-pound weight with 115.5 pounds of tension in the cable and 57.8 pounds of compression in the strut. We can take these and we can put them back onto our structural elements. And we know that this cable is going to have to be designed to take 115.5 pounds. Notice more than the weight that we're hanging off of it. And we're going to have a strut here that's going to have to take 57.8 pounds of compression. It's a symmetrical structure, so we can assume that the weight will be the same over here. And now the big question might be, well, what about the remaining cable? And we can do this in a couple of ways. We can take the vertical components of the 115.5 pounds in each of those cables, sum them up, and then figure out what the opposite would be. Or we can zoom out and we can avoid doing the math at all, because we can see here that we'll have two vectors that are 100 pounds each, and this cable is going to have to take the vertical component of both of those, which will be 100 pounds times 2, or 200 pounds, right? This is actually trivially easy because we only have the 2 vertical forces acting on the whole system. So we've done it, right? We have figured out the total tension loads in the cables, the compression load in the strut. We can use that to go ahead and design the cables, right? Size the cables once we know how strong the materials that we're using are. But we could also use this process to figure out whether we've got the best design option. For example, what if we have an option where instead of a 60-degree angle between those cables, we have 120 degrees, a shallower angle and a greater distance between the 2 weights? Well, think for a second what that might imply, remembering that we talked about the kind of shapes of triangles and the way that loads resolve themselves in them, and see if you can sort of guess where we're going to go with this. We have the same weights, 100 pounds, but this different geometry is going to necessarily change the way those forces resolve themselves within the structure. Now, the cable that's hanging from the concrete slab, that's not going to change, right? We still have 100 pounds down plus 100 pounds down. The cable here is going to have to still be 200 pounds up, right? The sum of those 2 weights, but in the equal and opposite direction. What's going to happen if we look at the free body here, analogous to the free body that we looked at in the previous example where the strut and the cable and the weight all intersect? So here's our free body, and let's do the same sort of thought experiment. What loads are acting on that free body? Well, first we have the weight of the anvil, and that's unchanged, 100 pounds. We'll have the force in the cable and the force in the strut. But notice that the force in the cable, because it's the only other vertical force acting on the free body, that cable has to take all of the vertical component of the 100-pound weight. And to get 100 pounds of up, we need, with this shallower angle, we need to go a lot further over, right? Because it's a shallower angle, we end up doing more horizontal work to get the same vertical work done. And when we do that, we're pulling that free body over to the right, and we need a larger force in the strut to push it back to the left, right? A vertical load here, the weight of the anvil, gets translated into a much shallower cable here, which means a greater load within the cable, and therefore a greater horizontal load within the strut, right? Shallower angles typically mean larger internal stresses to take care of the same external force. So here's our force triangle now, weight of the anvil, force in the strut, force in the cable. We could do it the other way around. We could go weight of the anvil, force in the cable, force in the strut, so long as the arrowheads and tails are all pointing towards each other. And now if we throw some trig at this force triangle to find the loads in the cable and the strut, we use a similar process, but we've got to use slightly different trigonometric functions. So ka toa. And we'll start now by trying to find the force in the cable. So we know the 60 degrees, and we know the 100 pounds, so we know the adjacent. We want to find the hypotenuse. We'll use cosine of 60. Cosine equals adjacent over hypotenuse. So cosine 60 equals 100 pounds, adjacent, divided by hypotenuse, force in the cable. We again do our algebra to move all of the knowns to one side, all of the unknowns to the other. We get 100 pounds over cosine 60. We do cosine 60 on our calculators, and we find that that is 0.5, and the force in the cable, therefore, is going to be 100 pounds divided by 0.5, or 200 pounds. Notice that the force in the cable now is twice the load that we're putting on that free body, right? So that change in the angle has had a huge impact on the load that the cable is actually experiencing. We can do the same thing, same set of operations to find the force in the strut. We can use either angle. In this case, let's use the 30 degrees, and we know the opposite. We want to find the adjacent. So 100 pounds opposite over adjacent, the load within the strut. Tan 30, we move over so that we get all of the knowns on one side, the unknowns on the other. Tan 30 is 0.577. And when we divide 100 by 0.577, note that again, we get a force within the strut that's actually greater than the load we're putting on the free body, right? So that shallow angle has had a big impact on both the cable and the strut. And we have internal stresses that are actually greater than the external load that we're putting onto the free body. So if we take the force triangle and we transfer it back to the structure and we compare it with the internal stresses that we had in the previous iteration, we find that we have much, much bigger loads than we had previously. And to a structural engineer, this is going to be a problem, right? They're going to have to almost double the size of the cables, and they're going to have to almost triple the size of the strut to handle these internal stresses if we want to carry the same load, right? There may be architectural reasons that this shape is necessary, but the structure is going to have to work a lot harder to successfully reach internal equilibrium in this arrangement than it would have in the previous one. Okay, so that is a brief look at how we can use translational equilibrium to solve for a relatively simple structure. In the next video, we will apply principles of rotational equilibrium, looking at moments and trying to see how we can use the notions of rotational equilibrium to give us some information about how a beam has to stand up in a similar way that we've looked at how the cable structure has to stand up.